So today we're going to go over a calculation making the assumption that light is a particle, and in this case we would call these particles photons. So as usual, why don't you read this question over and see if you can solve it on your own, and then come back to the video when you're done. So we have our light here that's a 100-watt light bulb, and it's producing some orange light at 600 nanometers. So question A is asking for the frequency of that light. So this is definitely a problem you should be able to do. It's a nice review problem. So we're just going to use our wave equation problem for this. So V equals F lambda. The speed of light is 3 times 10 to the 8th. And the wavelength in this problem was 600 nanometers. Okay, which is 10 to the negative 9th. Alright, go ahead and plug that in. You should get a frequency of 5 times 10 to the 14 hertz. Okay, second question's asking you, well, how much energy does that have? So this is where we're going to utilize our new equation, which is the energy of a single photon. So this we're going to say E is equal to hf, where h is Planck's constant and f is the frequency. So this is going to give us the energy of each individual photon. So recall the Planck's constant is going to be 6.63 times 10 to the negative 34th. And the units for this would be joules per hertz. Then we'll just go ahead and multiply by the frequency, so times what we get, 5 times 10 to the 14, and that's going to give us an energy of 3.32 times 10 to the negative 19 joules. So again, what that's telling you is each photon has 3.3 10 to the negative 19 joules of energy. Okay, and recall photons are just these little packets of energy, and so that's why this number is so small. It's a small, tiny packet of energy. Alright, how many photons are given off in each second? Okay, so letter C, what we're going to do for letter C is say, well, the light bulb was 100 watts. Now we're just going to go ahead and make an assumption that it's 100% efficient, so all the light given off is this 100 watts. We'll look at non-efficient items in the future, but we'll say that this is 100 watts, and remember the unit for watts is a joule per second. So it's giving off 100 joules of energy every second. Well, this is 3.3 times 10 to the negative 19. We could write this as joules per photon. So each photon's giving off this amount, right? So to calculate how many photons in 1 second, we're just going to use a simple dimensional analysis and say, well, this is 3.32 10 to the negative 19 joules per 1 photon. Alright, we're just going to simply divide by that amount. So 100 divided by 3.32, that's going to give us 3.01 times 10 to the 20 photons per second. Okay, and it's a huge number because each photon is a tiny, tiny packet of energy. So that means we're going to have a lot of photons per second. Okay, alright, the last problem, letter D, this is dealing with a new unit that I'm going to introduce here, and this unit is called the electron volt. And we're going to go over more of this when we get to our electricity unit, but in simple terms, this is essentially saying that this is how much energy we would give. So 1 electron volt is the energy we would give to, well, 1 electron if we put it under 1 volt of potential. So how much energy we give to 1 electron put under 1 volt of potential. So remember the charge of 1 electron, if you remember back to last year, 1.6 times 10 to the negative 19. The units for that was a coulomb. And for 1 volt, Remember, if we break this down into its bare unit, would be 1 volt, which is a joule per coulomb. So notice what happens here. We can say 1 electron volt is equal to 1.6 10 to the negative 19 joules. So the reason that we use this unit, this electron volt unit, is if you go back and look at the energy per photon up here, 3.32, 10 to the negative 19, this is a very, very small unit, a very small number. And so this just kind of helps give us more reasonable numbers to work with. So for example, let's go ahead and calculate this out. If this is 3.32 times 10 to the negative 19 joules, then this would be, we'll just go ahead and divide by the joules per electron volt, and that's going to essentially give us, what, about 2. Okay, 2.08 to be exact. So it just gives us a better reference of what we mean by these energies, these photon energies. They're very small, but it's about the equivalent of 1 electron put under 2 volts of potential. Okay. One last thing with this, actually 2 last things. The first thing is our Planck's constant, 6.62 times 10 to the negative 34, right? And that's joules per hertz. We can also write this in terms of Planck's constant, in terms of electron volts. And so if we go ahead and divide by 1.6, 10 to the negative 19, what you're going to get is 4.14, 10 to the negative 15. So this is just another version of Planck's constant. Sometimes you're going to want to go into electron volts directly and bypass having to do the conversion. In that case, you're going to want to use this number instead of this version of Planck's constant instead of this one. Okay, one final question. This is a conceptual question I want you to think about. What would happen, how would our problem change if we used a more powerful light bulb? So for example, if we used a 200 watt light bulb, so let's write this down. What would change if we used a 200 watt bulb? And there's really two things that could change. One would be the energy of each photon, because we're increasing the energy, right? This is 200 joules per second now. So I want you to think about what would change. The energy of each photon, or the number of photons. So in other words, if we increase the brightness of the bulb, would this cause each photon to have more energy? Or would this produce more photons? So think about that question. We'll go over that tomorrow.